But I'm really happy to see all of you here today. Thank you so much for coming. It's kind of a thrill to see so many friends. Thank you very much to the organizers and to Javad, who's always keeping me on track with sending in abstracts on time and things like that. And thank you to the Fields Institute for hosting this sort of long program now, which is kind of exciting, especially for young people. So I've given a version of this talk or pieces of this talk actually a number of times, but I thought there might be a lot of young people here today. And so my goal for today is to talk about what these polynomials are, to talk a little bit about the different kinds of research that have happened in relation to these polynomials, and to share some open problems, some which are very hard and some which I think are not so hard. So some work for people who might be looking for something to work on. Okay. So I'll talk about the context of the spaces. So Dirichlet-type spaces, of which the Dirichlet space is one of them. And I'll tell you what these polynomials are. So they're polynomials that solve a certain extremal problem. And then I'll discuss why we study them, how they're maybe interesting for cyclicity problems, which Tom referred to, how these optimal polynomials are related to orthogonal polynomials and reproducing kernels. I'm going to talk about some problems with their zeros. The zeros of the optimal approximants was one of the reasons that they were very interesting, in particular for some engineering applications. I'm going to talk a little bit about the decay rates related to these polynomials and some convergence and universality results. So what I'm talking about here is a kind of a summary of a host of research in the last 10 years or so, 10, 15 years. And you can find a lot of references and discussion of these topics in this survey paper that my student Ray Sentner and I wrote recently. That's going to appear soon, and you can find it on the archive. Okay, so let's go ahead and talk about what the spaces are first of all. So for a given real parameter alpha, I'm going to define these Dirichlet-type spaces. So these are analytic functions in the disk that satisfy, whose coefficients satisfy a certain growth property. So as Tom said yesterday, if I take this alpha is 1, actually he started just by forgetting the +1 here, and then he added the H2 norm. But if alpha is 1 here, you see that you get this classical Dirichlet space. So the Dirichlet space is one example of this set of analytic function spaces. So for different parameters alpha, we get different spaces. If I take alpha as 0, this disappears, this k plus 1 to the alpha, and I just get the Hardy space norm. And if I take alpha as -1, I get the Bergman space actually. So that would end up dividing this ak squared by k plus 1. And you could kind of guess, just looking at this progression from -1 to 0 to 1, that the spaces, as beta gets bigger, the spaces actually get smaller. So it's a kind of increasing set of spaces, reversing so when alpha is less than beta, the d beta is included in d alpha. So these spaces are really interesting. They cover a lot of situations. They're Hilbert spaces with the natural inner product that's given here. And you can see just from the definition of the norm that the polynomials are dense, right? The Taylor polynomials actually approximate the function in norm. So they're very good spaces. So this is the context that I'm going to be talking about. And if these k plus 1 to the alpha bother you, since we're in the week of the Dirichlet space, just think of this alpha as 1. Or if you want to go back to last week, you can think of the alpha as 0 and be in Java's situation. Okay, so what are these optimal approximants? They're polynomials, first of all. So if I fix one of these spaces, which means I fix a parameter alpha, and I fix a function and I fix an integer, I fix a function in the space, I'm going to say that Pn, this is going to be my optimal approximate, Pn is the nth optimal polynomial approximant of 1 over f. So it approximates the inverse of f in some sense, if Pn minimizes this quantity. So I look at all polynomial multiples of f for polynomials of degree at most n. Okay, I look at all polynomials of multiples of f for polynomials in polynomials of degree at most n, and I see which one approximates 1 the best. that one that approximates such that P and F approximates 1 the best, that Pn is the optimal polynomial approximant of that degree. So in other words, Pnf minus 1 is the infimum over this set of polynomial multiples of f. So what is this? This is actually just the distance between 1 and the space Pnf. This is a finite dimensional space. So that's just the projection, right? If I take 1 and I project 1 onto this finite dimensional subspace of d alpha, I get exactly Pnf. So that means that Pnf is the projection of 1 onto the space. It always exists and it's unique. Okay. So this polynomial depends on a lot of things, right? It depends on the space. It just depends on the function, and it depends on the integer n that I'm interested in. Okay. So from this, you can see that if I kind of factor out f, I can't really factor out f, but if I factored out f, I get Pn minus 1 over f is small in some sense. But of course, 1 over f might not be in the space, so this is not necessarily a direct approximation. So it's kind of an indirect approximation of the inverse of f. Okay. If there are any questions, by the way, just feel free to jump in. So why study these polynomials? Why are they of interest? What are they connected to? Actually, I didn't know this when I first started working on these problems with my co-authors that I'm going to talk to you about. But originally, these polynomials were introduced. They were called least squares inverses in H2. So for the Hardy space H2, Robinson in the 60s, in 1963, this is a quote from what he wanted to do. He wanted to find the inverse under discrete convolution of a finite length minimum delay wavelet that best approximates the unit spike. Okay, so what does this mean? So actually wavelets were not even really a thing at that time, but this was something that he was interested in. So what did that problem mean actually? So the problem was just for f a polynomial. So f looks something like this maybe on the circle. Let's say visualize it on the circle. The Hardy space H2. And so given a finite sequence of the coefficients of this polynomial, this minimum delay in this context, it means that the first coefficient is the largest coefficient of this sequence. Find another sequence. So for each n, I might be interested in finding another sequence such that the discrete convolution of these two finite sequences best approximate the unit spike, which means with a 1 in the first position in the little L2 norm. Okay, so what does that amount to? The discrete convolution basically is the sequence of coefficients that you get when you do the multiplication of this polynomial p that you get by forming the with the coefficients ak times the polynomial f that you get with the coefficients of f using bk. So actually this question is exactly minimize pf minus 1 for a fixed f for whatever degree you choose. So for each n. So it's actually the same exact problem. It's the problem in H2 and it's the problem for a polynomial, but it's the same exact problem. And they were interested in that. I'm not going to talk that much actually about the applications today. I've given a few talks on that recently, so I'm going to go to the more classical problems. Robinson, and then there's a whole host of literature after that. And a lot of people got interested in this, and in the engineering literature, it's a big thing related to filter design. And in the whole wavelet industry, people were really interested in approximating these unit spikes because those are related to approximating big sharp changes in signal, which the Fourier transform is known to not be very good at, right? So for example, in image processing, when you're trying to detect the edges of a face, you want to detect the sharp change from one region to another. So approximating the unit spike was an interesting problem for them. So that was kind of the flavor of the type of problem he was interested in. So that was early in the 60s. Now, why did I become interested in them together with my co-authors, some of whom are here today, Connie Liao and Daniel Secco and Alan Sola and Alberto Condori, and I started talking about these a long time ago in 2011. We were really interested in cyclicity, and actually we were interested in this Brown and Shields conjecture, which perhaps Tom will mention tomorrow. So So Tom already defined what it means for a function to be cyclic. He referred to it in terms of multipliers, but this is an equivalent definition. If I have a function in d alpha, it's cyclic if its polynomial multiples, the closure of all of its polynomial multiples, the closure in the norm of the space gives you everything. Okay, so sometimes people use the square bracket notation to denote, it's essentially the smallest z invariant subspace generated by f. Okay, so this subspace generated by f, if it gives you the whole space, in some sense, f generates the space. F is called cyclic. So it's very easy to see that if f is cyclic, that means you can approximate everything in the space, right? So you should be able to approximate 1 by polynomial multiples of f. And if you can approximate 1 by polynomial multiples of f, the optimal approximants are the fastest approximation. So they're going to approximate them also. So you can see that if f is cyclic, then the polynomial optimal approximate multiples of f have to approximate 1. But on the other hand, if the polynomial optimal approximate multiples of f approximate 1, then I can just multiply both sides by any polynomial, essentially. And since polynomials are dense, that means I can approximate any polynomial in d alpha, and that means I can approximate everything. So actually, another way of talking about cyclicity in this context is that f is cyclic in d alpha if and only if the optimal approximate multiples of f approximate 1 in the norm of the space. Is there a dog? My dog is in the background, but he's not barking, thank goodness. So we were very interested in talking about cyclicity for the Dirichlet space because we were really interested in this Brown and Shields conjecture, which is a very famous open problem, a hard problem, and it says the following. It's an attempt to characterize cyclic functions of the Dirichlet space, essentially. So if you have a function in the Dirichlet space, it has to be outer. We know from actually what Tom said already that cyclic functions in the Hardy space are outer, so it must be cyclic in the Hardy space for sure, because that's a bigger space. So if you take an outer function in the Dirichlet space and you consider the boundary 0, so I'm being kind of loosey-goosey about this, but we saw that f has boundary values quasi everywhere actually for the Dirichlet space. So if you take those boundary values that are the zeros of f, then the Brown and Shields conjecture says that cyclicity in D is equivalent to this boundary 0 set being not too big, and it's not too big in the sense that it has logarithmic capacity 0, okay? So the Brown and Shields conjecture is really only one direction of this, because we know that if f is cyclic, it's not too hard to prove that if f is cyclic, then the zeros have to have logarithmic capacity 0. The zeros have to be fairly small. It's kind of intuitive. We know for sure there can't be a 0 inside, as Tom just mentioned in his talk, because every polynomial multiple would reproduce that 0. But what happens on the boundary zeros, there can't be too many of them for sure. And so for sure, if f is cyclic, the boundary zeros must have logarithmic capacity 0, but the Brown and Shields conjecture is saying that that's actually equivalent. So we were really interested in that problem. Of course, that's a really hard problem, and all these really smart people, Fala, Kelly, Ransford, and many other people worked on this problem. So they have a nice paper. They have several papers, but one nice one in particular in 2009, if you want to get a feel for how hard this problem is. They sort of reduced the problems to certain special kinds of functions. And we decided, well, it's hard to solve the cyclicity problem, so can we study these polynomials Pn instead and get some information about the cyclicity from that route? So that was our original kind of goal and mindset. So just to give you a feel for what we were and were not able to do, in the Hardy space, as we already mentioned, f is cyclic if and only if f is outer. That's basically from Berling's result. Outer, there are many different definitions of outer. I think Javad talked about this the first week. One way to think about it is that certainly f has no zeros, and log of f mod f of 0 has this, oh, I forgot log here. that's kind of important. Sorry, there should be a log here. Is as big as possible. Usually you would have an inequality here less than or equal to. Okay, so this is as big as possible. But put the log here in your mind, otherwise that's not correct. In a paper in 2016 with Dima Havinson, Connie, Alia, Denis, Ekonal, and Sola, we were able to come up with a characterization of cyclic functions in H2. I didn't write the products, but basically what goes here is some complicated product that involves the zeros of the optimal approximants. So if some complicated expression involving just the zeros of the optimal approximants equals this quantity. So it's kind of analogous in some sense to the definition of an outer function. Of course, that's not very helpful because we already know what outer functions are in H2, but it was a step towards our desire to understand cyclicity from the point of view of the optimal approximants. So that was really all we were able to do there in that respect. Another interesting thing is that if f is inner, so every function in the Hardy space has an inner-outer factorization. Inner, one way to think about inner functions is that they're less than 1 in modulus inside the disk, and they're 1 almost everywhere in modulus on the circle. If the function is inner, then all the optimal approximants are constant. Okay, they're all the same. So they reduce to just a constant related to f. So optimal approximants can detect inner functions in some sense. And if I have a function in H2, which is an inner function times an outer function, it really only gives you information about the outer function times this constant. Okay, so that a little bit dashed our hopes in some sense that we'd be able to get information about cyclicity unless we somehow try to get information about the zeros of the optimal approximants. Okay, so H2 is one space where cyclicity is very well understood. It's not known still really in the Dirichlet space, a nice characterization in the Bergman space. It's not known in many other spaces. So one kind of open question, which is a little bit vague, is there some way to use the optimal approximants of a function to identify whether that function is cyclic in some of these other spaces? So that's kind of one kind of direction, possible direction of research. So as I said, Alberto Condori, Cornelia, Denis, Secco, and Alan Sola and I worked on this in 2015. We introduced these optimal approximants because we wanted to answer this question. And we didn't get that far. Really, the only thing we were able to do later was in another paper with Dima Havinson was involving the zeros of the PN. Okay. So let's now turn to another idea and talk a little bit about how do you actually calculate these optimal approximants and how are they related to other objects, classical objects in analysis and function theory. Okay, so let's suppose I have one of these Dirichlet-type space functions, monogenically zero. How do I actually get the Pn? Well, remember, it's the projection of 1 onto this space. So all I need is a nice basis for this space, right? For the Pnf, the curly Pn, the beautiful Pn times f. So I take a generating set for this space and I use Gram-Schmidt to get an orthonormal basis. So here's my orthonormal basis. So these phi k are sort of orthonormal polynomials in the sense that phi kf is an orthonormal basis of this beautiful Pn times f. And then I just write Pn times f in its Fourier series, in the basis that I've just created. So I take the Fourier expansion basically in this basis against this phi kf basis. But of course, Pn plus this orthogonal complement gives you 1. So this orthogonal complement piece doesn't interact with phi kf, it's 0. So this inner product is the same as just taking the inner product of 1 with phi kf. Okay, these are equal, right? Because this this perpendicular piece doesn't have any value, it's 0. But what is the inner product of 1 with phi kf? Remember what the inner product representation is. 1 just has the very first coefficient. So that's actually just A0, B0 bar, where the A0 is 1 and the B0 is the value of this function at 0. So this inner product is just pk of 0 bar, f of 0 bar. Okay, so if you put that together and you get rid of f, you actually get a formula for Pn in terms of these orthonormal polynomials. And there's this coefficient f of 0 bar, which comes into play. Okay, so these optimal approximants can be connected to these orthonormal polynomials in this way. Okay, now they're orthonormal polynomials in a kind of a weighted sense because they're orthonormal against f, right? So in the space, beautiful Pn times f. All right, so here's this formula for Pn. So I've kind of reproduced the formula for Pn times f, okay, where these pkf's are this orthonormal basis. So what happens if I take a polynomial q of degree at most n, and I multiply it by f, and I take the inner product of that with p and f? Okay, well, qf is in this space, right? It's in this space. So again, qf is orthogonal to this orthogonal piece. So if I just take pn plus this orthogonal piece, I get 1. So this inner product is, again, as before, just the same as the inner product of qf with 1. Same exact reasoning. And of course, that qf inner product with 1 is just the value at 0 of this polynomial times f. Okay. So if I take anything in the space pn times f, and I take the inner product of it against my optimal approximate times f, I get q of 0 times f of 0. What does that tell me? That tells me that this PNF is a reproducing kernel for this space at 0, right? Because if I take QF against that function, I get the value of QF at 0. Okay, so that means that Pn is not only connected to these orthonormal polynomials, but Pn times f is actually a reproducing kernel at 0 for this nice finite dimensional space. Okay, so there are a lot of things that are known about orthonormal polynomials, orthogonal polynomials, reproducing kernels, especially in the context of H2, for example. So we actually gained some information about these optimal approximants in that case. But I'm going to tell you something a little bit more general. But one particular point of interest, a lot of reproducing kernels in a lot of contexts often do not have zeros in the disk. So is there somebody not muted, perhaps? I don't know if that's, you guys are hearing that. Are you guys hearing that? Okay. So what can we say about these zeros of this object? At least the zeros of Pn is what I'm really interested in. Let's say even if f have no zeros in the disk. Do these reproducing kernels have zeros or not? All right. So let's see. Well, what happens if this reproducing kernel, let's call it little kn of z, had a 0 in the disk? Let's say it has a 0 at lambda, okay? So that means that I can pull out that 0. Okay, this is the 0 lambda, I don't know where it is, times some other polynomial of some smaller degree, 1 degree less, right? Because I pulled out 1 degree times f. Okay, so rewriting this expression by sort of multiplying this through and bringing it to the other side, I get that lambda qf is zqf, and then minus bringing kn over here. Okay, so lambda is the potential, is a 0. Let's say lambda is a 0 of kn. But look, this kn, this is my big kn z0. This big kn is the reproducing kernel at 0 for the space of polynomials of degree n times f. And this function vanishes at 0 because of this z, right? So that means if I take the inner product of these two things, I'm going to get 0, right? So these two guys are orthogonal, actually, okay? Because this guy reproduces at 0 and this guy vanishes at 0. But if those two guys are orthogonal, that means I have Pythagorean theorem, right? So that means I have this equality of norms. So here's my reproducing kernel, which is my Pn times f. Here's my 0 of my Pn. So let's suppose that I had some information about how multiplication by z acts on a space. For example, in the Hardy space, we know it's an isometry, right? Multiplication by z. So this would be the same as the norm of QF. In the Dirichlet space, this gets bigger, right? So suppose I knew that there was some constant such that multiplication by z was bounded below, essentially, in this context. Okay, so this would be larger than or equal to this constant times QF alpha squared. So for example, for the Hardy space, I can exactly write, and for the Dirichlet space too, actually, I can write 1 here for this C alpha. Okay, so then just rearranging that, I get that this 0 lambda squared minus this constant times the norm of QF squared is larger than or equal to what's left here. But this is strictly positive. This norm is strictly positive because it's some function, not identically 0 in the space. So that means this is something that's greater than or equal to 0. So that means that this thing is strictly greater than 0. So what does that tell me? That tells me that getting an estimate on how multiplication by z acts on the space is related to getting estimates on the zeros of these reproducing kernels, which is natural actually in some sense. So for example, for the Hardy space or the Dirichlet space, or actually any alpha bigger than or equal to 0, this 0 must be strictly bigger than 1. Okay, and in general, for any of the d alpha spaces, what we know is that this reproducing kernel can have no zeros inside this closed disk for whatever this constant happens to be. Okay, so just saying this again. So for the Dirichlet space, the optimal approximants have no zeros in the closed disk, and for the Hardy space and for alphas between 0 and 1, no zeros in the closed disk. It turns out that the zeros can get as close to the closed disk as possible. In fact, I didn't talk about it here today, but it turns out that the zeros of the optimal approximant are dense. Actually, they can approximate every point on the circle for the situation. For other d alpha spaces, when alpha is less than 0, for example, the Bergman space, this is my notation for the Bergman space, the zeros of Pn can come into D. If I go back, this constant is less than 1 for the Bergman space. That doesn't tell you for sure that they must go into this disk, the zeros, that there are some zeros that must go into the disk, but it tells you that there's the potential for that. Okay. Oops, sorry. But it's not very hard to show. You can come up with examples of zeros of optimal approximants that do indeed come into the disk. Okay, so they can indeed come into the disk. And so then that raises another set of questions. How far in can they come in? Right, so we know for the Dirichlet space and the Hardy space, they can come all the way as close to 1 as possible. They can't hit the circle, but they can get as close to the circle as possible. For the Bergman space, how far in can they come, actually? So there's this minimal 0 problem, which you can consider. So sort of what's the best, what's the smallest norm of any 0 of any optimal approximant for any function in the Bergman space? Okay, what's the smallest such 0? So that's a little bit of a more detailed question than looking at that C alpha, which is not a sharp, in general, it's not a sharp constant. So it's sort of it's a sharp problem. So we were able to solve that with Nazima Havanson, Connie Ya, Daniel Secco, and Brian Simonek in a paper in 2019. We solved that problem in a series of spaces that were similar to the Bergman space, but we weren't able to get it explicitly for the D alpha spaces with this norm that I gave you in this talk today. We had to actually slightly change the norm and consider some integral norms. But for the Bergman space, the smallest 0 is 2/3 root 2. And what you would get from this previous C alpha is 1/2 root 2. So that was kind of exciting. We were happy about that. So we got 2/3 root 2 is the minimal zero of any function in the Dirichlet space, in the Bergman space, and the extremal function, whose actually first order optimal approximate. You can reduce this problem to studying first order optimal approximants. The extremal function whose first order optimal approximate has a zero of this modulus looks like this. So it's actually a pretty nice rational function that has a zero pole outside the circle. And there are a lot of interesting problems in that paper, actually. These problems turn out to be related to orthogonal polynomials on the real line and to certain Jacobi matrices and eigenvalues of certain Jacobi matrices. So there's some questions in differential equations also that are related. So there are actually quite a few problems that we don't understand very well in this paper, which I'm not going to talk about more here. I'll just mention one problem, which is find these minimal zeros for some of these other spaces, for these negative alphas. That's not clear. In several variables, there are quite a few papers that were written in the engineering literature after Robinson published his work. I'm not going to talk very much about them, but one of the questions that I think is interesting is formulated as in a paper by Meredith Sargent and Alan Sola as the weak-Shanks conjecture. And the sort of weakest form of the Shanks conjecture, which is for the Hardy space of the bidisk. So if I look at the Hardy space of the bidisk, so I'm not really going to talk about exactly the definitions, but they're analogs of the one variable definitions, okay? So you can come up with a coefficient norm that's the same sort of analog in the Hardy space of the bidisk and define optimal approximants correspondingly. Meredith and Alan talk a little bit about how you need to choose your basis in some ordered way, right? Because if you have several variables, you have more choices about how to order your orthonormal bases. So you can pick some, depending on your ordering, you get certain different polynomials. But suppose you choose some natural ordering. If I start with a very, very good function, just a polynomial of two variables that has no zeros in the closed bidisk, then do these optimal approximants, does the same result that holds for one variable hold here, actually? So do these optimal approximants in this two variable situation, are they also zero free, even in the open bidisk? That's not known, okay? This fails in the Bergman space of the bidisk, and Meredith and Alan have an example, and they have a lot of examples in computations and sort of some interesting questions related to orthonormal polynomials. Okay, so that's one kind of open problem that's still out there. A lot of people in the engineering literature were very interested in these optimal approximants early on. I don't know if it ended up being very useful for them, but they were interested in the optimal approximants very early on because they used them to construct filters, and it was important for filters to essentially correspond to functions that have no zeros inside the disk. And so because these optimal approximants have no zeros inside the closed disk, they were good tools to have something that's called stability for filters in the engineering literature. So the engineers were interested in these polynomials for that reason, because they had no zeros in the closed disk in the context of the Hardy space when they took F to be a polynomial or some simple situation. Okay. Oops. Okay, now let's talk a little bit about another set of problems that really are not that much is known here. When I mentioned that Alberto, Connie, Danielle, and Alan and I were interested in working on cyclicity and didn't get very far at first, but studied then these optimal approximants instead, one of the things we were interested in was, well, how fast actually is that rate of decay of this PNF minus 1 for a particular F? So of course it's going to depend on the F, depend on the space. The interesting situation is actually an f that has zeros on the circle. So we were able to prove something only really for very good functions f. There are some isolated examples, but what we were able to prove for these d alpha spaces, when alpha is bigger than 1, Tom mentioned this the other day, when alpha is bigger than 1, these d alpha spaces become algebras. So you can see that the Dirichlet space, as Tom mentioned, is sort of, it's not an algebra, but it's on the verge of being an algebra. So just immediately past it, those d alpha spaces become algebras. So they're a little bit less interesting from this point of view. For the optimal approximants, we know exactly when functions are cyclic, they can't have zeros at the closed disk. So for our purposes, they were a little bit less interesting. So that we studied this situation for alpha less than or equal to 1. And we considered very, very good functions f that are analytic in the closed disk, so really good even on the boundary, and with all their zeros outside D. So if their zeros are actually outside the closed disk, then you can show, right, f has a power series expansion beyond the disk, and so then there's a really fast decay of this object. So that's actually a little bit less interesting. 1 over f will be well behaved in that situation, okay? But if 1 over f is not well behaved, in other words, if f has a 0 on the circle, then 1 over f doesn't necessarily, right, doesn't have a nice expansion, right, because there's a problem on the circle. So this rate of decay is actually a little bit slower. So for example, for the function 1 minus z, that's a typical cyclic function, let's say. So we were able to prove that the rate of decay is less than this growth over here. And in fact, we have, it's a sharp rate of decay as long as the function has a 0 on the circle. If the function has a 0 on the circle, this is indeed the rate of decay of this PNF minus 1 for these pretty nice functions, assuming it has a 0 on the circle. But Friquin, Mashregi, and Secco studied this problem for sort of more general weights. So in this d alpha, my weight's omega krk plus 1 to the alpha. So they had more general weights that satisfied certain conditions. So their theorem includes these d alpha spaces. And they studied this problem, the same problem. And I just wanted to mention it's pretty hard in general to compute these optimal approximants. So they computed them in certain situations, in particular for this function 1 minus the z, and they came up with a nice formula for this optimal approximant. And you can see it's a weighted average, basically, right? It's a weighted average of the Taylor polynomials for 1 over 1 minus z in some sense. Okay, so some of these optimal approximants pop up as weighted averages. And you can rewrite this expression for H2, you get this form. So this is a polynomial of degree n. And you can rewrite it. It kind of looks like a rational function, but it isn't really, because this polynomial here has a 0 of order 2 at 1. So this is actually a guy that cancels. Okay, it's not obvious from the way I've written it here. But this is kind of a nice closed form for this expression that you can actually just look and see where the zeros of this guy are for this particular example, for example, and they're all certainly outside the closed disk. Okay, so these guys also had some questions about rates of decay in these general situations. But most examples, so most computations of optimal approximants and most rates of decay for functions, especially functions that don't behave well on the circle, are open. So lots of possible particular problems to consider there. Okay. Another set of problems of interest has to do with convergence and this notion of universality. So for this Dirichlet space, for example, or any d alpha space, if f is cyclic, then we know that these optimal approximate multiples of f approach 1 and that this quantity goes to 0. Okay, we talked about that in the very beginning. And that implies, because of the way this norm behaves, that inside the disk, I have uniform convergence on compact subsets of the open disk. Okay, so point-wise, certainly I have convergence inside the disk. I have really, in fact, quite a nice point-wise convergence. So what about in the Dirichlet space, say, or in the Hardy space, where I know I have boundary values, or if I took a really nice function, like let's say a polynomial, that certainly has boundary values on the circle. What do I know about the convergence on the circle? Do these optimal approximate multiples of f still converge to 1? So is it still true that Pn of zeta converges to 1 over f of zeta? For zeta, let's just take the situation where f is a nice function. So f of zeta makes sense everywhere on the circle. For zeta, in the whole closed disk, except for the zeros, you shouldn't expect that they would converge at the zeros, right, of f, because this is 0 and this is 1. So certainly that can't be the case. But other than that, do I get convergence? Mirto Manolaki and Daniel Secco and I studied this question, 2020. Somehow this is missing here. This should be for the Bergman space A2. There's like a secret A here. Yes, indeed, this does happen. And we actually proved that this convergence if f is a really good function, okay? So if f is a polynomial with simple zeros that are all outside the disk, then certainly Pn of zeta converges to 1 over f of zeta, actually uniformly on compact subsets of the closed disk minus the zeros of f. That's actually what we proved. We proved that for H2 and for the Bergman space A2. I'm sure that it's true for the Dirichlet space, but we didn't prove that in our paper, so that's still something that could be done. It has to do with estimating reproducing kernels of the space, doing some computations. So that's a question. What happens in the Dirichlet space? What happens for slightly less good functions? We're pretty sure that the simple zeros is not important, that the zeros could have multiplicity. It's just that the computations get more complicated in that case. But I'm pretty sure that that's still true, that I have this nice convergence for good functions f. What if f is not a polynomial? What if f is maybe analytic in the closed disk? I think it's very likely that you would still have this nice behavior in that case. What about the opposite scenario? Okay, we know that functions in the Hardy space are sort of defined up to sets of measure 0. So crazy things can happen at one point, or in the Dirichlet space at one point, or in the Dirichlet space at sets of capacity 0, for example. So let's just look at 1 point for 1 second. What if I took 1 point on the circle? Is there an f in the Dirichlet space such that the optimal approximants for that f don't behave in this nice way that I just described, but just at that 1 point, right? So that Pn zeta doesn't converge to 1 over f of zeta, that it does whatever it wants, that if I take the closure of all the optimal approximants at that 1 point, I get everything, I get all of C. Okay, can that happen? So you would expect that to happen for not such good f, right? I just showed that for good f, for polynomials with certain, simple zeros, etc. That's not the case, right? These Pn of zetas converge to 1 over f of zeta. What if f is not so good? Could it be that I get everything as limit points of these optimal approximants? And the answer is yes. And in fact, there are many, many, many such functions. Many such functions. In fact, in a paper with Oleg, Ivry, Mirto, Manolaki, and Daniel Secco, a different paper in 2020, we proved, I'll state the result for the Dirichlet space. We proved a result for the Hardy space and the Dirichlet space. We proved that if you take a closed set on the circle of capacity 0, so this is kind of the gray zone, right? Because boundary values exist quasi everywhere. So crazy stuff could happen on these small sets. Then there exists a function in the Dirichlet space. So it kind of extends this idea of just 1 point. such that if you take any continuous function on this set E, now the set E is, maybe not so good, right? It has capacity 0. So continuous on this set E means what continuous on E means, but, E may have a lot of whole, E maybe is small. But no matter what continuous function on this set E I take, I can always approximate it using the optimal approximants, but maybe with some subsequence. Okay, so there exists a function in the Dirichlet space such that no matter which continuous function I take, there's always a subsequence of the optimal approximants that approximates G of E in the norm of this space, so in the sup norm, okay, on the circle in this sense, okay, in the sup norm. And in fact, there are many, many, many such Fs. Okay, so this is a kind of universality result. People talk about, refer to this F sometimes. This is a very particular kind of universality. So this F sometimes is called a universal function for this set of continuous functions. Okay, so a similar result holds for the Hardy space, where this is measure 0 instead of capacity 0. If you go to Bergman spaces, things are a little different, right? The uniqueness sets behave a little bit differently. You can have sets of positive measure, maybe now. Okay, they would have to also satisfy other conditions related to an entropy condition, which Tom talked about earlier with his, if you look at the complementary intervals of E, the sum of the lengths of those intervals times log of 1 over the lengths of those intervals have to behave in a certain way. And in fact, that has to be true for all subsets of E. For sure, something else besides this positive measure. But in the Bergman space, we have the chance that maybe this universality result would still hold. So in other words, is it true that if I take a closed subset of the circle, does there exist a result? Does there exist a closed subset of the circle with positive measure such that this such that there's some universal function for the optimal approximants for the Bergman space? Okay, we know that such results hold for Taylor polynomials. So is it also true for optimal approximants? So that's one example of an open question. Of course, for any of those other D alpha spaces, that's unknown. All right, and I'll stop there. Thank you very much. And in my talk, I've attached a bunch of references, so I can attach this in the chat if people want to see it. Thank you very much.
Thank you, Catherine Beneteau. Wonderful talk. Is there any question for Catherine? And did I ask one question when you talk about your result with Manolaki? I asked the zeros can be on the boundary on T.
Yes.
Okay.
Yes, the zeros can be on the boundary on T. Yes.
But simple ones.
Yes.
Okay.
Yes, simple zeros on the boundary. I think it's probably still true for double zeros also. We just didn't prove, we didn't prove it in that case. The interesting situations are always when the zeros are on the boundary. Usually if the zeros aren't on the boundary, things are easier. Because basically, if you have a good function, 1 over f is a good function in that case. So you can kind of do some things there.
Any further question or remarks?
Let me try to attach my file. He attempts to attach my file.
Please. If there is no further question, let's thank Catherine again. And we resume in about 7 minutes.